I'm Walter Lewin. I will be your lecturer this term. In physics, we explore the very small to the very large. The very small is a small fraction of a proton, and the very large is the universe itself. They span 45 orders of magnitude, a 1 with 45 zeros. To express measurements quantitatively, we have to introduce units. And we introduce, for the unit of length, the meter, for the unit of time, the second, and for the unit of mass, the kilogram. And you can read in your book how these
Right. Working out resultant forces and equilibrium forces using moments and a pivot point. So here's my example, an L-shaped bracket of some sort, and we need to work out because of this force here and this force here and this force here, what is the resultant force of all of them and the direction, so the force, the angle, and also because we've got a pivot point, is it going to go anti-clockwise, is it going to go clockwise? And then we'll also consider the equilibrant, which is just the equal and opposite. So there's my little diagram. It's not to scale. I've got a 4 kilonewton coming this way, and I'm calling anything going this way positive, anything going up positive, anything coming down and to the left negative. That's a bit orange. So I've got a 4 kilonewton force there, a 3 kilonewton at an angle from the horizontal, and a 6 kilonewton coming down there at 50 degrees from the horizontal. So first of all, we've got to work out the vertical and horizontal components of these forces using that force and that angle. This one's an easy one because it's coming straight horizontal, so we'll just there's no angle, so it's horizontal only, there's no vertical component. So here's a little table that I like to use. F is my forces in kilonewtons, 4, 3 and 6, 4, 3 and 6. That's angle, so the angle from the horizontal. Obviously 4 has got 0, 3 has got 30 and 6 has got 50. And to break it down into the horizontal and vertical components, the way I do it is F cos theta, horizontal, and the vertical component F sine theta. There are other ways we can do it, but that's the way I like to do it. Thank you, Teeps, or any of that. So there's my fourth. There's my 4 kilonewtons force. Obviously, it's only going horizontal. There's no vertical component. So it's only going to be 4 really here, because it's only going horizontal, it's not going vertical, so there's going to be a 0 and a 4. It's going to the right, that's why I've got a plus 4. We can still stick it in a formula, so we'll do F cos theta, F being the force and theta being the angle, which is 0 in this case. So in the calculator, I'm going to do 4 cos 0, gives me 4 to the right. Don't forget it is kilonewton, so be aware of that. And then for my vertical component, F sine theta, F sine of 0. So we'll do 4 sine 0, 0. Obviously. So that's my kilonewton force, the 4 one sorted out. Number 3, there's my 3. So I'm going to work out now what is the force in this direction, vertical, and what's the force in that direction, horizontal. This one's going up, so it's going to be positive. This one's going across, so it's going to be negative. There's my force, there's my angle. There's my force, there's my angle. Horizontal is going to be F cos theta. So F cos theta. In your calculator, 3 cos 30. 2.59, 2.59, 2.6. It's going to the left, because we know it's going to the left. It's going to the left. Horizontal, going to the left. We call that negative. So that's why I got a negative number there. The vertical one's going straight up, so it's going to be positive. So vertical one, F sine theta, F sine theta. So F sine theta, 3 sine of the angle, which is 30, gives me 1.5. 1.5 is the answer. 1.5 kilonewtons. It's going up. 1.5. That's why I got positive number. So we've got 1.5 going up and 2.6 coming across. So that is breaking the 3 kilonewtons down into its vertical and horizontal component. You could go the other way. If I was to pull something 1.5 kilonewtons up and 2.6 kilonewtons this way, the resultant force would be 3 kilonewtons that way at 30 degrees. So that one's sorted. Here's the next one. I got 6 kilonewtons. There's my angle, there's my force. I'm going to break it down into that vertical one. It's coming down, so it's going to be negative. This horizontal is coming across. It's also negative. So there's my force, 6 kilonewtons, and there's my angle. So 6 kilonewtons, there's my angle, 50. So horizontal, F cos theta, vertical, F sine theta. So 6 cos 50, 6 cos 50 in your calculator. 6 cos 50. 3.856, 3.86, I've gone up, look. It's going to the left, so it's going to be a negative. So we've got 3.86 coming that way. And then the vertical one's coming down, so I'll get a negative number again. And we're going to do F sine theta, where F is 6 and theta is 50. So 6 sine 50. 4.59, 4.6. It's coming down, that's why I've got a negative number there. Direction 4.6. So there's that. So that 6 kilonewtons has got a horizontal component of 3.86 and a vertical component of 4.6. If I was to pull something downward at 4.6 kilonewtons and to the left at 3.86 kilonewtons, the resultant force would be 6 kilonewtons coming this way at 50 degrees. So we've done that bit, we've broken each force down into vertical and horizontal. Now all we've got to do is add them up. So I'm going to add that one up, that one up, and that one up. Don't forget we've got negatives. I'm going to add that one up and that one up. That'll give us our total horizontal and total vertical. So in your calculator, I got 4 plus minus 2.6 plus minus 3.86. That'll give us our total horizontal, 2.46, 2.46, 2.46. So the resultant horizontal is 2.46. It's a negative number, which means it's going to the left. So it's something like that, 2.46 that way. All right, because it's negative. Horizontal. Same with the vertical, we've got to add these up. So there's a note there, ignore that. So 1.5 plus minus 4.6 equals bang, 3.1. So the resultant vertical is 3.1. It's got a negative number there, negative number, which means it's coming down. So it's something like that. Don't forget these are kilonewtons, so make sure you put at the end kilonewton and kilonewton, which gives us then 2.46 coming that way and 3.1 coming that way. Obviously you could do that just to close it all off. So we know that due to that force, and that force, that this thing, the resultant force on it, is coming down this way at that angle there. Look. So we need to work out this resultant force here and that angle there using that and that. Don't forget, the minus just means direction, so you haven't got to put minus there and minus there, as long as you know that minus comes that way and minus comes that way in our notation. So we need to work out now resultant force, the direction and the angle. So there we just worked out 2.46 and 31. We need to find this resultant force here. So that length is 2.46. That length has got to be 2.46. This one's 3.1. That one's going to 3.1. So we can now work out that hypotenuse, which will give us the resultant force. Using Pythagoras, which we should know from a previous life. So r squared is going to be 3.1 squared plus 2.46 squared. 3.1 squared plus 2.46 squared. Oh dear. 3.1 squared plus 2.46 squared. So then obviously that's a square, so we need to square root all of this. So this resultant force is going to be the square root of all of that. So in your calculator you can do this. Make sure you get the right brackets in the right areas. So square root 3.1 squared plus 2.46 squared equals 3.95. I've got up to 3.96. So the resultant force is 3.96 kilonewtons in that direction, coming down. So now we know the resultant force. Alright, so all these forces here, that one and this one, are going to result in a downward force of 3.96 here, 3.96 coming down. We'll now work out that angle, which we can do using a bit of SOHCAHTOA or a bit of trig. We know that's 2.46, we know that's 2.46, we know that's 3.1, and we know that's 3.1. We also know that that is 3.96, because we do. We now need to work out this angle here. That's my angle, that's my opposite side there, that's my hypotenuse, that's my adjacent. So you know them all. I'll use cos. So cos of the angle, so cos is going to be adjacent over hypotenuse, cos of the angle. So the adjacent we know is 2.46 and the hypotenuse is 3.96. Obviously, if that was wrong with us, then we'd be wrong. But so I'll do both ways. I'll do tan as well. Look. So A over H, 2.46 over 3.96. Obviously, you've got to inverse cos it. So we can do this. Shift, inverse cos, do a bit of that. 2.46 divided by 3.96, do a bit of that, do the magic. 51.59, 51.6 degrees. Which means the angle in there, is about 51.6 degrees, or 52, whatever you want to say, 51.6 degrees. So the resultant force is 3.96 at 51.6 from that horizontal. You can use tan, because we can. You can use sine as well if you want to, but if you want to use tan, we can use tan. So tan is going to be opposite over A, opposite, it's getting messy now, opposite over A. So there's my opposite and there's my adjacent, opposite over adjacent. So tan is opposite over adjacent. Don't forget you got inverse tan as well. So get rid of that. So same thing as before, inverse tan, do a bit of that. Where's that? So 3.1 divided by 2.46. Come across, close the bracket, press equals 51.56. 51.6. So that's the angle calculated and the resultant force calculated. So the resultant force is, let's get rid of that perhaps. The resultant force is 3.96 and the angle from the horizontal in there is 51.6 degrees. So there we are. So it's going to be coming down something like that, 3.96 kilonewtons and 51.6 degrees. That's the resultant. We now need to work out the moment because we need to know which way this thing is spinning. Is it spinning clockwise or anti-clockwise? Because it's on a pivot, so it could be going that way or it could be going that way. I'll call anti-clockwise negative, I'll call clockwise positive. You can call it either way if you want to. So I'm going to use each force now and I'm going to go to this pivot point because that's our pivot point. So what I've done is I've labelled each force which we just calculated. So there's the 4, there's the 1.5, 2.6, 4.6 and 3.86 which have come from here. 4, 2.6, 1.5, 4.6. So I've labelled them to make it easier. I've also labelled the distances because don't forget moment is force times distance. Force times distance to the pivot. There's our pivot. Force, 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 distance, distance. So what I've done there, I've labelled the 4, which is that one there. 1.5 is there, 2.6 is there, and so on. So number 4, let's just get rid of some of this stuff. Get rid of this. We go and use the 4 to the pivot point. Moment is force times distance. So moment is force times distance. So there's my force coming this way like that. There's my 4. And my distance to the pivot point is simple like that. Pivot point is there, so force times distance. So 4 times by this, which is 3. So 4 times by 3 is 12. Horizontal, it's only going horizontal. 4 times 3 is 12, and this force here, that 4 will try and spin this thing clockwise. That's why I got clockwise there. Positive. Obviously it's only going horizontal, so it hasn't got a vertical moment, so we can forget that. So that one's alright, nice and easy. Let's see if we can get a bigger one of that. Nope. Obviously can't get the different side over then. Alright. That one. Next one I'll do is the 1.5. The 1.5 is coming up, so it's only got a vertical moment, so 0 horizontal. 1.5 is coming up, vertical moment. So I'm going to look again at force times distance to this pivot point there. So there's my force, 1.5 coming up like that. 90 degrees away, bang, Force times distance, which again is 3, so force times distance is 3. Here's my force, line of my force. Distance is 3. 1.5 times by 3 gives you 4.5. That 1.5 will tend to try and spin this thing clockwise about that point. That's why I've got a positive number. So I'm calling clockwise positive. So 1.5 times by 3 gives me a 4.5 clockwise moment. Obviously, it's a kilonewton per meter, so don't forget to put that in. No horizontal, so there's no horizontal moment. That one's done nice and easy. And I'm just going to do the same thing now for the rest. Get rid of this, make it a bit easier. So 2.6. 2.6 is going horizontal, so it hasn't got a vertical moment, it's only going horizontal. So again, draw your line, 2.6 go, there's my line of my 2.6. Force times distance, again is 3. Force times distance from there to there is 3. So 2.6 times by 3 is 7.8. That force there will tend to try and make this thing go that way, which is anti-clockwise. That's why I got a negative number. So 2.6 times by 3 gives you 7.8. It's trying to go anti-clockwise, negative, anti-clockwise. There's no vertical thing to it, so the vertical moment is 0. So we can ignore that. So that one's alright. And we'll do the same now for the 3.8. And we'll do the same thing for the 4.6. So there's my 3.86. So 3.86 is here. There's my line of my force. Horizontal moment is only going horizontal, so we'll ignore the vertical. So 0. Force times distance, in this case, that force there, that 3.86, is on the same line as that pivot point. So there's no distance away, there's no distance. So you've got to have a distance for a moment to work. That is like pulling on a hinge of a door or pushing on the hinge of a door. The reason why a door opens is because you've got a distance away from the hinge. If you just pulled on the hinge, you're not going to open the door, you're going to pull it off its hinges. There's no moment, there's just a force. So in our case, we've got a force times by 0 because there's no distance. So 0 distance means 0 moment. So there's no moment produced by that 3.86 about that point A. So that one's nice and easy. And then the last one's 4.6. The 4.6 is going vertical, so we're going to have a vertical moment. It's not going horizontal, so there's going to be no horizontal moment. So again, force times distance. There's my force, 4.6 coming that way, and my distance here again is 3. So 4.6 times 3. Force, distance, 4.6 times by 3. 4.6 times by 3. 13.8. This force here will tend to make this thing go anti-clockwise about that point. That's why I've got a negative number there. 4.6 times by 3 is going that way, it's going anti-clockwise, that's why I've got a negative number. So that's all of the moments from each of them forces sorted about that point A. Now as before, same as the resultant force, we've got to add them all up. Don't forget we've got negative and positive numbers, so we've got to add up. We're going to add up, let's go red for a laugh, we've got to add up all of these, we've got to add up 12, 7.8, 4.5 and 13.8. So the total horizontal moment is going to be 12 plus minus 7.8. So we'll do 12 plus minus 7.8. 4.2. Don't forget the kilonewton per meter, because it is kilonewtons really, and moment is Newton meters, which means 4.2 is positive, which means the horizontal moment is clockwise. So the horizontal moment is trying to push it clockwise. So the vertical one now is going the other way, it's fighting the horizontal, so we'll add 4.5 plus the minus 13.8. 9.3, 9.3. The minus just means it's going anti-clockwise. So the vertical moment is anti-clockwise 9.3. That's the moment sorted. One last bit, we've got to add up the total moment. So all I'm going to do is add up that to that. So 4.2 plus minus 9.3 will give me the total moment. This will tell me if it's going anti-clockwise or clockwise. So 4.2 plus minus 9.3. 4.2 plus minus 9.3 equals 5.1. So 5.1 is a minus number, which means it's going anti-clockwise. Kilonewtons per meter. Which means that whatever this is, it's going to be spinning anti-clockwise at 5.1 kilonewtons per meter. The resultant force is 3.96 at 51.6 degrees. The last bit we got to do now is work out where that is, because we need to draw the line of action on this thing here. We need to draw the line of action on here. So we know that it's going coming down 3.96. So it's coming down at, well, what color should we have? It's coming down at 3.96. Something like that. With the angle really in there, that's the angle in there. It's got to be this side really, because it's got to spin anti-clockwise. So it's got to be this side of this to make it spin anti-clockwise. So we know that, we know the angle, we need to find this distance here now. The perpendicular distance from there. So the perpendicular distance, I don't like that colour. The perpendicular distance of the resultant force from point A, we can simply use this. Moment is force times distance. We know the moment, we know the force, we don't know the distance. Rearrange this. So moment over force will give me distance. We know the moment is 5.1. We know the force, it's 3.96, which is there. I've left the k's out because they cancel out. You can put them in if you want to. So the resultant force divided by the moment gives me 1.29 meters. So that's the perpendicular distance. So now on my whatever it is, L bracket. So we need to draw the line of the resultant force and the equilibrant. So there's my resultant force. It's coming down like that at 3.96 with an angle of 51.6. So 3.96 at 51.6. At 5. Oops. We know it's going 5.1 anti-clockwise, so we need to draw this line here, this side of the point A, because this thing is going to try and make this thing spin that way. If it was this side, it might go anti-clockwise. If it was over here, it would tend to spin it anti-clockwise, but we know it's going anti-clockwise, so the force, wherever that is, roughly has got to be on the other side of that pivot point. It's got to be here to make this thing spin that way. It can't be this side because that would then tend to make it go clockwise. So the resultant has got to be the left of A to make sure it goes anti-clockwise, because we know it's going to go anti-clockwise because we've worked it out. And then that perpendicular distance is 1.29, so the 1.29 comes from there. 90 degrees from there, 1.29, not to scale. That's the resultant force, and the equilibrant, you can just draw it equal and opposite the other way. So it's going to be the same angle in there, but a different force going in the opposite direction. So that would be the equilibrant. So that's the easy bit to do. Really. So it takes a couple of steps. Use a grid like that, do it nice and slowly, and everything should be okay. Hope that makes a bit of sense. Over and out.